Hello and welcome to this new video. Today we are going to talk about the Linux kernel 6.11. So this is a part 2. If you want to see the part 1, it's in the description, but let's get started. Now I feel that AMD is getting a little jealous. We haven't talked a bunch about them and we're going into graphic and audio. So of course we're going to talk a bunch about AMD. So let's start with the AMD RDNA 4 GFX 12 driver, which is good enough to be enabled by default for future GPU. So we now see default support for those RDNA 4 GPUs, and it was also added to AMD KFD, which is the AMD kernel fusion driver. It's the driver that takes care of ROCm or OpenCL. So pretty much when you want to do something else than process an image through your GPU, if you want to compute or do AI, you're going to use that driver. So now you have that capabilities to use those RDNA 4 GPUs with the Linux kernel. We've also seen a few fixes from the AMD side, which is good news. We've seen the fix of a long time regression with the high definition audio driver when using the newer GPU, the newer Navy GPU, using HDMI audio. So the problem was that if you were using any amount of CPU while trying to listen to audio, you would have stuttering, you would have skipping. Turns out that they were using two patches instead of one, a old one and a newer one. So you had a patches that was using WC pages, so write combined pages. So those are a special type of pages that you can write multiple times to, and that will burst into storage later. And also it was using scatter gather IO, which is a command where you can do multiple reads or write into a single call with devices containing an IO-MMU. So the IO-MMU being input-output memory management unit, meaning your GPU when it tries to communicate with the rest of memory on the system. So in reality, in that situation, you shouldn't use any WC pages. You should only use scatter gather IO because you have an IO-MMU with your Navy GPU. And when you remove those WC pages from the code, well, everything goes well. So it was that simple, just using one fix at a time. And we have another fix from the AMD GPU side of things, where they addressed a massive bug that was doing massive CPU spikes while clearing VRAM. So since 6.10, since the last kernel, we see that if you're playing Dota 2 on some AMD GPU, you're seeing divided by 5 performance. So if you have 500 FPS, you now have 100 FPS on Dota 2 or pretty much any game. So it's a pretty funny one. I want to see the Arch guy just just having a field day with this one. But anyway, that's a good thing that they fixed it. And let's go ahead and talk again about fun facts. Fun fact, AMD graphic drivers account for 15% of the kernel. Yes, 5.8 million lines. Crazy, right? I still cannot believe how much code is in just graphic driver and just AMD. The big reason why AMD is so heavy is because they have those big headers to their code files. So that's why there's a lot more weight to AMD drivers. Doesn't actually mean that they have more code in it.
All these lines of code, they're coming in by the millions and millions. No one has ever seen anything like it, and it's a very bad thing. What's happening is a disgrace.
We also see initial work on the graphic driver for the XE2 integrated graphic in Lunar Lake CPU and also the next-gen Battle Mage cards. We're seeing initial support on the DRM file, while on the Mesa side, the driver is mostly done. Now let me just take half a second to explain what is DRM, what is Mesa. So when we're talking about graphic driver on Linux, there's two possible options of what type of driver it is. There's the DRM, there's Mesa. DRM is the part that is in the kernel. DRM stands for Direct Rendering Manager. So that's a kind of a layer, a compatibility layer that is supposed to be there so that when you have something like X or Wayland that want to communicate with your GPU, X and Wayland doesn't actually know what type of GPU you're running, and it doesn't actually care, right? It just wants to render some really simple things to the screen. So it will communicate with that DRM piece of code, and then the DRM piece of code will go through the necessary drivers to be able to communicate with your GPU. Now, if you need some more graphical capabilities, like, I don't know, playing a game, you would need the Mesa side of things, which is the big GPU driver that allows you to play games and to have most other features that we all know and love. Now, I say Mesa side of things, but in reality, it could also be a proprietary driver because Mesa is just the name of the group of the open source drivers manager people. So when we're talking about a driver that's open source, we're pretty much talking about a Mesa driver because 99% of graphic driver that are open source are under the Mesa umbrella. Now, while we're talking about Lunar Lake, they added some new features into the kernel. They added panel replay and content match refresh rate. Now, for content match refresh rate, it seems that it's just a renaming of something that already existed, VRR, variable refresh rate. So we don't really know what it changes, but panel replay seems like a feature that should already exist for an eternity. I didn't know that it was really that modern. So it turns out you need DisplayPort 1.5 to be able to use panel replay, and panel replay is exactly what it sounds like. It's just telling the screen that you should replay the same image that was sent right before to be able to save battery life. I was under the impression that a simple HDMI cable could do it. And it's kind of surprising that we're losing battery life for nothing since forever. So good news that we're going to have support for that new standard soon. Still going with Intel, we have their Xe kernel graphic driver, so their current integrated graphic and graphic card that we see a lot of improvement on, and we also see initial hardware monitoring support so that we can now have a little clue about what's going on in there. And we also see the initial support for their accelerator driver when talking about the VPU NPU, meaning Visual Processing Unit, Neural Processing Unit. So pretty much when we're talking about images processed by AI, they have some special chips and card for that. So now you're going to have support for that. So we have support for their hardware scheduler. We have better profiling capabilities. We have better firmware handling. Pretty much we have everything across the board for them. So it's good news that we can see that better support from Intel. Well, Intel's not really doing that great right now. I'm sure you know it. But they actually don't do that great even in the Linux kernel, because we see from their Habana Labs side of things, which is their AI team, they have one of their big driver maintainer that left. He didn't disclose why he left, but he left Intel. So that's sad for you. And they also added their accelerator driver that is called Gaudi 2D, and we actually have no clue what the D stands for because we already have Gaudi 2, but now we have 2D and it doesn't change anything, but I guess we have the D now. So thank you, Intel. Thank you. Don't you think that NVIDIA is getting a little jealous by now? I think so. So now we have the Nuvo driver. So we're talking about the open source driver of NVIDIA graphic card that now has NVReg registry dword support. So those dwords, registry dwords, are there to send some commands to be able to fine-tune configuration, do some debugging, some experimenting with the GPU. That was already something that existed inside the proprietary driver, but now we have it inside of the open source one. So it's always good news. We also see some work into the DRM panic infrastructure. That's the part of the code that allows for a blue screen of death on Linux. So it allows now monochrome logo support, selectable font, and dumping the actual kernel panic message to the screen, which is useful. We also see a new monochrome TV mode added to DRM, so now we're able to support a new, old, obscure monochrome TV mode. Thank you, Raspberry Pi dev, for making our lives a little bit more weird every day. And now let's just run through the two new SoCs that we have support for. We have support for the X185, that's the Qualcomm Adreno GPU found in some Snapdragon X1 laptop SoCs, and we also see the Panfrost DRM driver that now supports the MediaTek MT8188 SoC. So if you know what they are, you must be happy right now. Now let's talk about virtualization, where AMD is leading the charge. We see again more work on SEV-SNP, which we talked about in the last kernel release, and we see also work to the SVSM, so the Secure VM Service Module. Now, just a quick recap, the SEV-SNP is a way to do virtualization where your memory is encrypted, what the CPU does is encrypted. So it's made in order that the host, even if the host gets infected, you cannot get any leak from the VM. So the VM is always safe because it's only communicating with the hardware and the firmware and not the software. So that makes things as safe as possible. So we have more and more support for that. And the SVSM is pretty much just an add-on onto that technology, where you can add your own pipe to some other firmware. So if you want to add capabilities, for example, for a virtual TPM, so you know that chip that's supposed to hold your secrets, hold your keys, well, you can now through that SVSM service. And we actually see some integration of the SEV-SNP, so that's the big news. We see KVM actually implementing it with their KVM guest, and QEMU also supports it. So we see more and more support coming in for that SEV-SNP. Good on you, AMD. That's really good. We also see VMware that creates their new VMware Hypercall API. So it's a new API that seeks to do pretty much all the same thing that we were talking earlier. So it seeks to plug into SEV, which is the precursor to SEV-SNP, and TDX, which is the same thing on the Intel side. So VMware is trying to standardize the way that it communicates with the kernel, because before, VMware pretty much has a bunch of small commands all across the kernel that are really hard to manage, and right now they just want to fill it out inside of one subsystem to make it as simple as possible to upgrade. So now let's talk about memory, and to make things as simple as possible, I'm going to explain a little bit of the basic of memory in the kernel. So inside of the Linux system, memory is allocated into pages. So everything is divided into pages. Those pages are normally 4 kilobytes of size. So when we're talking about memory in Linux, we're always talking about pages. There's some times where we need way more memory than 4K, or way less memory than 4 kilobytes. So all the system that we're going to see always attempt to either cut a page or grow a page to be able to optimize it as much as possible. Now, there is some really good benefit to try to grow a page, because there's something called a TLB, a translation look-aside buffer, in your CPU. The translation look-aside buffer, what it does is it saves the location of the last 64 pages that you've used. And when I say 64, that's actually the number of pages that a modern CPU can hold inside it. So the TLB will hold the location of those 64 latest pages, and it will be able to quickly go find them. And all of the other pages will be a little bit slower. The reason why we would want to grow a page is because we want to take advantage of this TLB as much as possible. So if we can optimize the quantity of page that we use, we can also optimize the quantity of TLB storage that we will use, thus being able to have faster memory. So let's now get into the changes that happen to the kernel. We can see that first of all, we have a big fix for the slab system. Now, slab is one of those systems that allows to cut a page into multiple smaller buckets. So let's say that you only need 200 bytes for your system or your program. You're not going to use a full page for that. That would be ridiculous. So what you will do is you will ask slab for only those 200 bytes, and he will cut a page into a smaller 200 byte size, and then he will give one part to you. So the problem is that before you could throw some bad data into that slab storage, and if you would have a bad part of the kernel that would be written where you would have an uninitialized value, well, the uninitialized value would of course pick up the data from the slab bucket and it would reuse it, thus giving a chance for some process to get greater privileges because of that vector of attack. So of course, now it's been patched. The way that they did it is they segregated the bucket. So now you cannot throw memory into the same bucket than the bucket that the kernel used. So if you're a kernel service, then you're going into the kernel bucket. If you're a user service, well, you're going into the user bucket. So now you have those two separate buckets for slab. Now, still talking about memory, we have a rewriting of the write-back code that gave us a better readability. So when we're talking about the write-back code, we're talking about the ability to write data that is considered dirty. So when we're talking about dirty in memory, we're talking about memory that's not written yet to the hard drive. So memory that is waiting to be written to a hard drive or to some permanent storage. So there was some rewriting of that write-back code, and now it has better readability, and it also fixed one possible overflow bug that could happen, so that's always good news. We also see a continued folio conversion. I saw a little bit of Z-swap that was changed and swap code. Now, when we're talking about folios are one of those memory construct, which I was talking a little bit before, those that are bigger than a page. So folios are just, you could think of them as bigger pages. So they're there to take less space in the TLB because they're bigger pages and they can take more memory while taking only one place in the TLB. While we're talking about TLB, there's also small optimization to the core TLB handling code. So that's good news because that's speed across the board that will be improved. We also see multi-size THP support for anonymous shared memory that can yield significant improvement around page fault latency. Let's just talk about the first two words here, multi-size THP. THP stands for transparent huge pages. Huge pages are just pages that are bigger than your standard 4K pages. So that size is dictated by the CPU. So the CPU may be able to allow 2 megabyte huge pages or maybe 1 gig huge pages. So there's different possible huge pages depending on the CPU. Transparent huge pages is just the ability to do it transparently. So you don't need to actually make some quick special code to be able to use those huge pages. It will just dynamically allocate the huge pages if you're using that amount of memory. And multi-size is kind of an add-on to that technology where now we can use partial size of those huge pages because, like I've said before, those huge pages are set by the CPU. So if you have, let's say, 1 gigabyte huge pages and you only need 512 megabyte of memory, you don't want to declare that big 1 gigabyte pages. That would be ridiculous, right? So with multi-size THP, you can now declare those partial size memory in between the huge pages that you could do before and the standard page size that you also had before. So of course, that gives us better latency. And while we're talking about transparent huge pages, we can talk about the reclaiming of those pages because there's been some rework in the reclaiming of lazy free transparent huge pages. When we're talking about lazy free, We're just saying that these huge pages were declared by our program or by our system to be a part of memory that we're not using anymore, but we're not going to explicitly free it right now. We're just going to tell the system, hey, I'm not using it, and when you have time, free it. So they've done some fix, and now it can be freed way faster. So 10x faster. We have a 10x speed up on that one. And while we're talking about better things in life, we have Daemon, the Data Access Monitor, which is a cool little tool inside the Linux kernel. We often see its implementation. It's called Damo. That's a program that you can use in user space, but Daemon is there to kind of give you an idea of what's going on with your DRAM. Where is the memory allocated? How efficient is the placement of that memory or that memory? And now we have the capabilities to even see those DRAM optimization or efficiency of the placement inside of Compute Express Link or PCI Express attached DRAM. So we can now see more and more things with our good old Daemon. So now let's switch on to security, where x86 Intel has a good idea to be able to get more performance out of your older hardware. There is a vulnerability called Spectre BHI, which requires you to have some hardware to be able to fix. If you don't have the hardware to do it, you can have a software version, but the software version has some pretty huge performance drawback. So what they did now is that they added a command where you can apply those mitigation, those fix, only to virtual machine, meaning that if the only part that is untrustworthy on your system is the things that you host, then you only apply that new fix and not the complete software fix, so that you can get the performance benefit of not using it onto the host, but only using it onto the VMs, which is pretty smart from Intel for giving us that solution. And while we're talking about smart, we can talk about the control flow integrity module that we use that can now be set at compile time. So we can choose between fine IBT or the kernel CFI, the kernel control flow integrity, to be able to make our kernel more secure. Now remember, the control flow integrity is there to confirm that one part of the kernel is really communicating to the part that it's supposed to the other end. So the difference between the kernel version and the fine IBT version is that the fine IBT is an hardware one. So fine IBT, hardware, kernel CFI is the kernel version, it's all software. You can choose between them at compile time, which makes a lot more sense than using a boot command, which could potentially be changed by an attacker. So that's always good news. And that's just like the fixed bug that we have with landlock. So landlock is a tool that is there to restrict the number of writes of a process. So you can say, hey, I don't want you to have network access, or I don't want you to access that part of the file system. So landlock is really there to sandbox whatever process you want to. Now the problem is that if you leave the fork and the key CTL access to that process, well, the process could just fork itself out of landlock. So it's a little bit like you lock your process and your process just warps a clone out of the garden that you've made for the process. Of course, that's a big no-no. You don't want your lock process to get out of containment. So that was fixed, and that's pretty funny to me that you could, for a moment, just fork yourself out of a lock. They also fixed the x86 32-bit version of KPTI. Turns out the kernel page table isolation wasn't really that good on 32-bit because it could lead to some failure in memory management. Now, KPTI was there to fix vulnerabilities like Meltdown, It segregates memory. So if you have that kernel memory and you have that user memory, well, both of them are going to be separate in order that the user cannot guess some secret from the kernel part of the memory by using some of the meltdown vulnerability. So the 32-bit version wasn't that well made. It's been patched. Good for us. We also have the kernel memory sanitizer that now supports S390 architecture. So the kernel memory sanitizer is just a quick tool that is there to see if a value is uninitialized. So you remember earlier with the possible attack to the slab memory system, it can all be prevented if the devs use kernel memory sanitizer to check their code. Now let's talk about RISC-V, which now has support for stack leak. Now stack leak is a really special subsystem. It kind of patches everything at the same time. It patches stack depth overflows, uninitialized values, and info exposures. So all of those fixes are done in a very simple manner, but it's still something that takes some amount of performance. That's why it's not enabled by default. But the way that it goes about it, it's when you make a system call, when you use a kernel function, what stack leak will do is it will poison whatever data comes in. So if you have an uninitialized value, it will make sure to replace that uninitialized value and initialize it with a special data. And after that, when you're done with your values, it will make sure to rewrite all the memory with that special value called poison. So by doing that, they ensure that no memory can come in that would be dangerous and no memory can come out that could be leaked. So that's really important in some circumstances. It's good that we have a tool for that, and it's good also that we have support for it on the RISC-V architecture. Now let's go on to cryptography, where we have some change from Intel and AMD with AVX 512 and AVX 10, which now has major optimization to it. We have some good performance change there. And of course, when talking about cryptography, we can talk about random number generation. More precisely, let's talk about getRandom command, which was now included in the VDSO. Now, the VDSO stands for Virtual Dynamic Shared Object. So it's a small shared library that is automatically mapped in the memory space of all the user space application, meaning that all applications that run on Linux have access to the VDSO. And the reason why you would want to add a command there is that when you try to communicate with the kernel, you have a latency there because you're communicating with the kernel, because you need to upgrade to kernel space and then throw that back to the user space. It makes everything a little bit longer and a little bit slower. But in that case, it's far more than a little bit, because we see 15-time performance gain in random number generation, which of course is crazy, right? It's rare that we see a 15x in anything. So it's good news that we have it. And of course, when we're talking about anything library, the GNU-C library has added support for that, meaning that when you compile with the latest GNU-C libraries, you will be able to get advantage of that new getRandom command that's now in the VDSO. Now let's talk about hardware, and to make it a little bit less monotonous, we're going to do a quick speed run of the hardware section of this review. So let's start with the Compute Express link, which is a standard that is used to add abusive amount of memory to server that is now being more and more implemented within the Linux kernel. We can now have a CXL maturity map on the documentation. We also have the new power sequencing driver subsystem that allows us to power up different part of components in order to prevent driver clashes. So it can be really useful when we're talking about Qualcomm Wi-Fi Bluetooth card, because they can sometimes have issues, and it fixes those issues. We also see support for more ASUS motherboard and the temperature sensors that are on it, and support for more power supply on the hardware monitors. We also see fan speed, temperature speed, and LED driver for Chrome OS embedded controller. And while we're at it, let's talk about the driver that was added for the image signal processor on the Raspberry Pi 5 that can do 4K 60 FPS, by the way. There's also a bunch of network driver that we're not going to talk about. We also have some x86 based Apple MacBook Pros that will now fake being identified in the EFI as Apple Inc., as this is the only way to enable both GPU at boot and not only one, for some reason. Thanks, Apple. While we're talking about x86, we've now removed the ability to do fake EFI memory maps. So when we're talking about memory maps, we're talking about the initial small part of memory that is changed by the motherboard or by the CPU in order to transfer some information to the kernel. So what you could do with those fake EFI memory map is you could actually fake that memory map so that you can have different information than what was written by the firmware. Now you can understand how that's not really a good idea, considering that we're in the era of confidential VMs and all of those things. So in a world where we're trying to trust as much as possible the hardware and the firmware that we're using, being able to change it on a whim isn't really a good idea. We also added support for a bunch of audio hardware, including the one included inside the Intel Panther Lake CPUs. We also have enhanced support for Qualcomm Snapdragon X1 Elite and Plus SoCs, and we've added drivers related to a bunch of ARM SoCs and RISC-V boards. We can talk about specific laptops though, like the Asus VivoBook S15, the Lenovo Yoga Slim S7X, and the Lenovo ThinkPad T14S Gen 6, and also while we're at it, why not the X1 Microsoft Surface Laptop 7 that all use this Snapdragon X1. Now, the big difference between all of them isn't really with drivers, it's most of the time with the device tree. Now, the device tree is that information that's in the firmware most of the time of ARM device that gives the information to the Linux kernel of where and what is connected to the CPU. So it's in the name, a device tree. It gives you all of the information, what's connected to it and what's going on the board of the computer. Now we also see MIPS IQ6 support, so that's a chip for self-driving. Good news. We have also USB and Thunderbolt upgrade, but nothing major on that point. We see the beginning support for the Kiba CP500 system FPGA, which is used for automation and manufacturing. We also have a better SATA link power management, because before we had the same system that was used for SATA and eSATA, and now that the external SATA is managed separately from standard SATA, we were able to change the power management mode. So before we used the keep firmware setting, and now we've set it to medium power with device initiated power management. The big reason why we are doing that switch now is because with external SATA, if you don't keep the keep firmware setting, you don't have the ability to do unplug. Of course, that's not really something that we want to remove from external SATA, because that's the only way that it's used 99% of the time. So now that eSATA is managed separately and that eSATA can keep that keep firmware setting, well, there's no issue there to be, so we can now save power on all our SATA drives. We also see more added to the HID driver, the Human Interface Device driver. So we see the Asus ROG Ally X support being added. We also see support for the XP Pen Deco Mini 4, the Trustmaster Boeing joystick, the keyboard backlight of some Intel-powered T2 equipped Macs. So yes, a bunch of new human interface device. We also see a bunch of things with HID and BPF, but I don't care to talk about it. So we're going to talk about Dell instead. So let's talk about the Dell PC driver that adds fan mode control and platform profile handling with the new Dell PC Extra driver. And on the HP side, we have the WMI driver, the WMI being an ACPI specification that allows for communication of hotkeys event and some configuration from the BIOS. It's mostly a laptop thing. So the HP WMI driver that now fixes the ACPI platform profile switching on various HP Omen and HP Victus laptop. On the Asus side, with that same WMI driver, it now handles the ZenBook 2023 camera LED disable indicator. And on the ARM side, we see the Lenovo Yoga C630 embedded controller driver that has now been upstream to be able to improve the Linux support of that aging ARM laptop. We also see more AMD Zen 5 CPU model added to Linux, along with some of them in the power management framework and the power management controller driver for configuration needed to make them work. So that's all for the hardware part of things. It was fast, wasn't it? So now let's talk a little bit about the benchmarks that are coming out from this release. We can see that on the AMD side, it's all going great. So either on Threadripper and on Ryzen 9, we see performance getting better from this release, which is good news because sometimes, yes, it happens. We have a Linux release where the performance goes down. That can happen when we need some big security patch for some reason. But in this release, we really are going in the right direction. And we also have some benchmark on ARM64, which we pretty much see the same thing. We have good result going up on everything ARM64. Now the interesting part here is that Phoronix made the test also with the 4KB page size and the 64KB page size, where we actually see how much performance gain we can get from a 64KB page size, because yes, that can be modified on some CPU, and if you recompile the kernel. Now what we see is that 64KB of page size is pretty insane. It gives us a really good performance gain, but you need to keep in mind that that performance gain is there because we are using the hardware to the max. That's the goal of a benchmark, right? So under normal circumstance, you're probably not seeing much performance gain if you're using a normal machine in normal ways. But if you're using something that does really heavy image editing or any kind of image processing really, or anything that will use a lot of memory, well, then you have a lot to win to go on that 64KB page size. Now, if you're interested and you have an ARM64 CPU, you should really look into your distribution, because some distribution have some supported 64KB page size kernel available for you on LTS. Yes, some example would be Ubuntu and Red Hat that have those kernel available to you and that are updated and patched with the latest security patches. So if you want to take advantage of them, you can. Of course, like I said, it's an ARM64 only thing, because on x86 you cannot even think about changing that page size. So this is it. I hope you enjoyed the Linux kernel 6.11. So yes, there was a lot to talk about in this release. Now, of course, this video couldn't be made if it wasn't for Phoronix, Linux Weekly News, and of course, the devs of the Linux kernel. So I hope everyone enjoyed. If you did, of course, leave a like, subscribe, and of course, I like your comments, so do them. And take care.